What does the divergence of magnetic field lines near the ends of a current carrying straight solenoid indicate? Here within inside you see the lines are straight and parallel, but as they move out they diverge, which means the distance between them increases. This clearly indicates that there is a decrease in the magnetic field near the ends of the solenoid, because the distance between the lines increase, and hence we can say the field becomes weaker. Identify the poles of a magnet in the figure. Now if you see here, the direction is given. That means the lines, they merge here. So this must be the south pole, and where they emerge, where they come out from, is a north pole, because we know the lines move from north to south. So they come, here is the north, they come out from the north and they merge in the south. So this would be the north pole and this would be the south pole. Why is an alternating current considered to be advantageous over a direct current for long range transmission of electric energy? Alternating current can be transmitted without much loss of electrical energy to a distant place, hence it is advantageous. So the advantage is AC current, there is less loss during transmission than the DC current. Identify the region where the magnetic field around a current carrying solenoid is uniform, and it's uniform inside the field, inside the magnet. Here in the diagram you can see inside the lines are straight, uniformly spaced, the distance between the lines are the same, but when it comes out you find the distance between the line keeps on increasing. So it becomes weaker. As we move away it is weaker, but inside the solenoid it is uniform and strong and stronger. Two circular coils P and Q are kept close to each other, of which coil P carries a current. Will some current be induced in coil Q if P is moved towards Q? Give a reason for your answer and name the phenomena involved. Now when this coil P, it carries current because it is connected to a battery, is moved towards coil Q, remember that P also has a magnetic field around it. There is a magnetic field around P, and as P moves towards Q, the magnetic field associated with Q will also increase. Hence a current will be induced in Q. In Q will have a current induced because Q will be now in a changing magnetic field. Because as P is moving towards it, the Q will experience an increase in magnetic field. So when P is moved towards Q, the current will be induced in Q because the coil P will carry a magnetic field around it. So when it is moved towards Q, it increases the magnetic flux around it. Hence a current is induced. This phenomena is called electromagnetic induction. What happens if coil P is moved away from Q? Now if it's moved in the opposite direction away, so the magnetic field now associated in Q due to P will decrease as it moves away. So here, if P is moved away, the magnetic flux around Q will decrease and the current will be induced but in the opposite direction. This is just like moving a magnet towards P, like moving, suppose you have a magnet here, it moves towards Q, or you have the same magnet that moves away. You will find that a current is induced in Q. But instead of a magnet here, now we have a current carrying coil, and a current carrying coil also acts as a magnet. So every time P is moved towards Q, a current will be induced in Q, and when it is moved away, a current will be induced in Q but in the opposite direction. State few methods for inducing current in a coil. We can induce a current in the coil by moving a magnet away or towards the coil, by moving the coil away or towards the magnet, rotating a coil within a magnetic field, or changing the magnitude of the current. In all these ways, we change the magnetic field around a coil and a current is induced. Compare a permanent magnet with an electromagnet. The first point is permanent magnets are not very strong. They cannot be produced. Very strong magnet cannot be produced. But if we want strong magnets, very strong electromagnets can be produced. Then second point, for permanent magnet, its strength is fixed. Here the strength can be changed by changing the current through the coil. Another one about polarities. In a permanent magnet, polarities are fixed. Here polarities can be reversed by changing the direction of the current. If we reverse the direction of the current, the polarity of the magnet also changes. The north becomes the south becomes the north pole. Then we have permanent magnet. They cannot be immediately demagnetized. They do not lose their magnetic properties very quickly. But an electromagnet can be demagnetized immediately. Just stop the current and it stops behaving as a magnet. And last, the example of a permanent magnet is a bar magnet, and a temporary magnet would be like a solenoid, a copper wire bound around in a circular coil is a solenoid. That's an example of an electromagnet. A current carrying conductor is placed perpendicular to a uniform magnetic field. What happens to the displacement of the conductor if amount of current increases, or if a horseshoe magnet is replaced by a weak horseshoe magnet? Let's go to the principle first. If I have a magnetic field, this is a magnetic field, and if there is a current carrying conductor placed in this magnetic field, we already have learned it experiences a force. It is pushed, it is displaced. And if you recollect, this force is given as BRL sine theta. Means if the current increases, the force also increases. If the magnetic field becomes stronger, the force also increases. Now let's get back to the question. A current carrying conductor is placed perpendicular to a uniform magnetic field. What happens to the displacement of the conductor if amount of current increases? Now if the current increases, the force increases. And if force increases, definitely the displacement will be more. The current will be pushed, the conductor will be pushed stronger. So the displacement of the conductor will increase on increasing the current. Next is, if the horseshoe magnet is replaced by a weak magnet, means if the magnetic field is decreased, you'll definitely agree that the force also will decrease. So if field is less, the force is less. If force is less, displacement is less. So will decrease using a weak horseshoe magnet. So displacement also will decrease. Here I have drawn this diagram to recollect. Here we have a horseshoe magnet. This is a horseshoe magnet, and there is a magnetic field moving from north to south, and this is a current carrying conductor placed in the magnetic field. It will experience a force. So repeat again, a current carrying conductor placed in a magnetic field experiences a force. A circular metallic loop is kept above a wire AB as shown in the figure. So here we have a current passing, and there is a loop kept above. What is the direction of the induced current produced in the loop if the current flowing in the straight wire is steady? If we have a steady current, so steady current means steady magnetic field or constant magnetic field. And if the magnetic field is constant, do you think current will be induced in the loop? There will be no current induced. Why will there be no current induced? Because for current to be induced, we need a changing magnetic field. Now next is, if the current is increased in magnitude. Now if they keep on increasing, the current is changing. Now because it is changing, induced current will be produced. As long as the current is steady, there will be no current in the loop. But if the current in A keeps on increasing, now there will be a changing magnetic field, an increasing magnetic field. Increasing magnetic field means there will be a current induced in the loop. What is the pattern of a magnetic field due to a circular coil carrying current? So here we have a circular coil carrying current, and it produces a magnetic field. And if you notice the magnetic field here, it goes upwards, the current, and then comes down. And if you use the right hand rule, here it's in this direction, while this side it is in the opposite direction. So this is the figure you will have to draw to show the pattern of a magnetic field due to a circular coil. So once again, this is a circular coil where the current is flowing in the clockwise direction by using right hand rule, thumb rule. We find the current will be here anti-clockwise, while the magnetic field on this side will be clockwise. We use right hand thumb rule. What is meant by magnetic field lines? Magnetic field is a region around a magnetic material in which the force of magnetism acts. It is a vector quantity. It has got direction as well as magnitude. Why don't magnetic field lines intersect? Or do they intersect? No, magnetic field lines never intersect. They can never intersect each other. If they do, then it would mean that at the point of intersection there would be two directions of magnetic field, which is not possible. So here's a magnetic field line, and at every point the field line direction at this point will be here. At this point the direction of the field line will be a tangent to the curve. At this point it would be again a tangent to the curve. But what would happen if they were to intersect? So suppose they were intersect, this never happens, but if they were to intersect, then there would be two tangents. That means a compass needle would have two positions, but this never happens. This never happens. So we say the field lines never intersect because at every point the magnetic field has got only one direction. State the purpose for the following. The right hand thumb rule. If you recollect, the right hand thumb rule tells where do we use it. If there is a current flowing in a conductor, we know a magnetic field is produced around it, and this is given by the right hand thumb rule. In this case, you will feel the magnetic field is in the anti-clockwise direction, but if the conductor current is in the downward direction, then you find the magnetic field lines will be in the clockwise direction. So the right hand thumb rule is used to find direction of magnetic field around a current carrying straight conductor. Next is Fleming's left hand rule. Now here is a picture of Fleming's left hand rule. It is used for a force. If we have a magnetic field, and in this magnetic field, if we place a current carrying conductor, we get a force X on this conductor, and the direction of this force is given by Fleming's left hand rule. So here we've written Fleming's left hand rule helps in understanding the direction of magnetic force acting on a current carrying conductor. And to recollect, if the forefinger gives the field, the middle finger gives the current, then the direction of the thumb will give you the motion or the force, direction of the force. Then Fleming's right hand rule. Fleming's right hand rule is used for induced current. Here we have Fleming's right hand rule. If this is the movement of the conductor in a magnetic field, if a conductor moves in a magnetic field, a current is induced, and the finger gives you the induced current. The center finger gives you the induced current. So here Fleming's right hand rule helps in understanding the direction of induced current when a conductor moves in a magnetic field. What is the pattern of the magnetic field due to a current carrying conductor? Now we know this is a current carrying conductor, and the magnetic field will always be concentric circles. In this case, by the by the thumb rule, right hand thumb rule, the direction will be anti-clockwise. But if the current is downwards, again the magnetic field lines will be concentric circles, but in this case they will be clockwise. So here's a diagram for it. This is the current carrying conductor, and we have concentric rings. Since it is in the downward direction, the magnetic field will be in the clockwise direction. So you can say, what is a pattern? You can say the pattern are concentric rings. So we can say the magnetic field lines are concentric circles with center on the conductor. The diagram below represents magnetic field caused by a current carrying conductor. Identify the nature of the coil. By now you would have guessed the coil must be a circular loop like this, because here you will have one set of, and then there will be another set, and that's exactly what they have drawn here, and then this will be here, right? And in the center, you know, they're almost straight lines. That is why in the center here the field is maximum, because all the magnetic field lines are in the same direction. So for this the answer is What is the nature of the loop? The nature of the conductor is a closed loop. Why are magnetic field lines closed loops? Because they start from the north and they go to the south, outside, and inside from the south to the north. So they are closed loops. You hear north to the south and inside from south to the north. Magnetic field lines are closed curves because they originate from the north pole and end in the south pole. But inside the magnet, it is directed from the south to the north. So they become closed loops. Draw magnetic lines around a bar magnet. Now here is a diagram for the magnetic lines around a bar magnet, and this is the activity from your textbook that you need to learn. You need to take a compass and a bar magnet, place the magnet on a sheet of white paper fixed on a drawing board using some adhesive material, and then you have to keep your compass closed. And when you keep your compass closed, you mark your north and your south here. Then keep your compass again to the next position and it will remain in this way. Mark your north and your south. Then again keep the compass in another position here. You will mark the north and the south. Keep repeating this process. Keep it in this, it will remain in this position, north and the south, and you keep repeating this same process. The compass will keep follow this path. All you need to do later is join all these points and you'll get a magnetic field line. You can read this, you can read the activity. This gives you direction. If it comes for a 4 marks, you've got to write this entire activity with the diagram. Explain the meaning of electromagnetic induction. Induction in the term of electromagnetic induction. So here, producing or induction. Induction means producing of electric current due to a changing magnetic field. This is important. Changing magnetic field is called electromagnetic induction. Now next is, what factors does this induced current depend? 3 factors on which the induced current depends. 1, the relative motion. It's a relative motion between the magnet and the coil. More is the motion, greater is the motion, greater is the current, induced current. The induced current also, remember, is maximum when the direction of motion of the coil is at right angles to the magnetic field. We can also say the induced current depends on number of turns in the coil. More are the number of turns in the coil, in the primary coil, more is the current induced. It depends on the strength of the magnet used. It depends on the speed by which the magnet is pushed into the coil. If the magnet is pushed faster, there will be more induced current. Then the next point they are saying, name and state the rule used to determine the direction of induced current. And the rule is Fleming's right hand rule. The rule is stated on page 235, and make sure that you study it. The next is, give a practical application of electromagnetic induction, and the application is an electric generator. In an electric generator, a coil is moved in a magnetic field and produces current. Coil is moved in a magnetic field and this induces current.